Okay, so we're going to look at intersection of two planes. In this case, we see that the normals are not collinear. So n1, the normal of the first plane in Cartesian form is 4, -2, 3, and n2 is 3, 1, -1. Because we can identify that those are not scalar multiples, we know that these planes are not going to be parallel and they're not going to be coincident. So the only other choice with the intersection of two planes is that these planes would intersect and form a line. So the line that they form, we know if we are looking at the vector form of a line in 3 dimensions, that there's actually an infinite number of possible representations of that line. So I'm just going to write it out here as the line being our point. Remember that we have our position vector to the point, and then a direction vector, t times some other vector. So that we know we've got our position and our direction, and there's an infinite number of choices for each of those. So this one here can be any point on the line, and this one can be any scalar multiple of a vector in the direction of the line. Because there's actually infinite number of options for that, we are going to choose kind of arbitrarily to help us solve here, that we're just going to choose the point that crosses the xy plane. So I'm just going to put a 0 in for the z coordinate of the position vector, and I'm just going to put a 1 in the position of the z coordinate of the direction vector. We know that any direction vector will work as long as it's some scalar multiple of this. So I'm just kind of arbitrarily choosing the scalar multiple where that's 1. Helps us out a little bit with the math. And again, this can be any point. I'm just arbitrarily choosing the point where the z value would be 0. So from here, I know that I can have the parametric equations from this line, that I would have x equals something, y equals something, and z equals something. And we don't know information about our x and y yet, but I would know that z would equal 0 plus 1t. So 0 plus 1t, or just z equals t. So again, that's pretty arbitrary. I forgot my t can be any real number there. So again, it is arbitrary. There's no particular reason that we do the z. I'm just keeping that consistent with the notes in the textbook and my examples. But you could choose any number here for x, y, or z in each of those two vectors and come up with an expression for that variable. So here I'm coming up with an expression z equals t. It does just make it a little bit easier. Then we're going to go up to our original equations of the two planes in Cartesian form, and I'm going to use elimination. So I'm going to use the first equation, which is 4x minus 2y plus 3z minus 5 equals 0. And I'm going to take the second equation multiplied by 2, just so I line up my y values both with the same value there. So multiplying the second equation by 2, I get 6x plus 2y minus 2z plus 14 equals 0. And if I add down here, I'm going to cancel out my y's. So I get 10x and no y's there, which is good. And then plus 1z plus 9 equals 0. I can then solve for x in terms of z, and I'm going to use this value here that I know my z value is a t because of the arbitrary choice I made up here, that I was going to choose the position vector where z was 0 and the direction vector where z was 1. So I'm going to say let z equal t. So 10x plus t plus 9 equals 0. And then isolating here, x would equal negative t minus 9, each of those divided by 10. So that's my parametric form of this line in terms of the x variable. So I could write that back up here. I've got x is negative 9 over 10 minus 1 over 10 t. Just kind of rewriting different order. That from there, I can use the second equation. That's a little bit easier to find the y. So I'm going to say 3x plus y minus z plus 7 equals 0. And I want to find the value of the y for this line in parametric form. I'm going to rearrange first, I guess. So you could put y equals negative 3x plus z minus 7. And then I know I've got my parametric form of the line. I know my x value and I know my z value. I'll just substitute those in here. So then y equals negative 3 times negative 9/10 minus 1/10 t plus z, which is just t, and minus 7. And then we'll just simplify that out. So 27 over 10 plus 3 over 10t, and I'm going to common denominator here, plus 10 over 10t minus 70 over 10, and hope I don't make any little mistakes here, but I should get negative 43 over 10 plus 13 over 10t. So that gives me the y value in the parametric form as well. So negative 43 over 10 plus 13 over 10t. I can then take this, and if I wanted to rewrite it in vector form, so the equation of the line of intersection of the planes would be negative 9 over 10, negative 43 over 10, 0 plus t times negative 1/10, 13 over 10, and 1. Okay, with t being any real number. The key here is really that this is just kind of an arbitrary decision that makes your math a little bit easier. There are an infinite number of possible answers, but if you let one of the variables, usually we pick z, equal to our t, it helps simplify the solving a little bit.